Good afternoon. Thanks for joining us for the second webinar in the Emerging Technologies Information Session series. My name is Amy Poles, and I'm moderating today's webinar. So I work for the USGS, where all of my time is dedicated to the Pacific Northwest Aquatic Monitoring Partnership, or PNAMP for short. PNAMP, along with StreamNet, co-led the planning of this webinar series, and the planning group included 13 other people from a variety of organizations. And I'm joined today by Eric Suring from the Oregon Department of Fish and Wildlife, who's been an instrumental part of the planning group for this webinar series, and he inspired today's lineup. So Eric will be helping with speaker introductions in just a bit. And to help keep my computer running smoothly, I'm actually going to turn off my camera and incoming video. So give me a second to do that. All right. So this is today's agenda. After I wrap up the welcome, we'll do a quick icebreaker, and then we'll hear from the presenters. And we are planning on 30-minute presentations with about 5 minutes for questions immediately following each presentation. And then we'll have 10 to 15 minutes at the end of the webinar for additional questions or open discussion. But first, some quick tips on navigating the meeting platform. Please do mute yourself when you're not speaking. If you're on the phone, you can use *6 to mute and unmute yourself. And if you're using your computer for audio, you can mute and unmute yourself using that microphone icon on the toolbar. And so you can get to that toolbar by hovering your mouse over the meeting window, and that should bring it up. And if you're having issues or have questions for the organizers, feel free to use the meeting chat, assuming you can get to it, which you can access by clicking on the conversation bubble on the toolbar. And then when we get to the Q&A, if you have a question, you have the option to either type your question into the chat, and again, you get to the chat using the speech bubble icon, or you can click on this hand icon, and that will raise your hand, and my team will assist me in keeping track of that, and we will ask you to unmute yourself to ask your question. Okay, so just for fun, we want to know a little something about you. So we're going to do a quick poll using Mentimeter. So if you would all take a second and open up the chat, you'll find a link to a poll. And so my coworker Sam is going to put a link in there. And again, to get there, hover your mouse over the meeting window, get the toolbar to show up, click on that speech bubble icon, and then from there, you should find a post from Sam. Let's see, I'm going to go do that myself. And I see that it is in there. And if you are having problems getting to the link in the chat, you could also just go to menti.com and use the code that's at the top of the screen. And it looks like people are finding it successfully. I see 39 results so far. I'm going to give it just another second, and then I'll reveal the results. Let's see. Right. Whoa, yes. So far, we've got 2 in the lead for sure. We've got R2D2 and Wally. I'd have to say, I agree. I think R2 is probably my favorite robot, but it looks like everybody got at least 1 vote. All right. Well, thanks for humoring me. You know, we'll be using live polling again, so this is kind of a warm up for later, but we appreciate it. You know, we went deep into your psyche with today's question, so thanks for sharing. All right, so I'm going to pass the microphone over to Eric Suring while Kain takes the presenter role and gets his slides up.
Hi, I'm Eric Suring, the Unoccupied Aircraft Systems Coordinator for the Oregon Department of Fish and Wildlife. Thanks to Amy and all the people at PNAMP and the whole crew, the panel, for getting this webinar series together. And thanks very much to our speakers today, Kain Kutz and Lauren Burns, for sharing their work. You know, the technology, processing, and analytics with UAS and area monitoring is in continuous development, so it's great to hear how other people are using it. So I met Kain Kutz at the huge AFS-TWS joint meeting a year ago, or maybe a decade ago, it's hard to tell now. And I saw his presentation and it was like, what? You can do that with imagery? So I'm happy to have him here today to share some of his classification magic with us. Kain graduated from the University of Iowa with a BS in environmental policy and planning and an MA in geography. And with his experience on remote sensing and object-based image analysis methods, he's been working as a contractor with Red Castle Resources at the U.S. Forest Service, his Geospatial Technology and Applications Center, where he's recently been evaluating UAS for resource mapping applications for the Forest Service, as well as developing training to teach others how to use UAS for resource mapping. Today, Kain will present on using UAS imagery to assess a suite of riparian and geomorphological metrics. Thank you, Kain. You have the helm.
So, like Eric said, my name is Kain Kutz, and I'll be obviously the presenter today. The second portion of this presentation is going to go over a kind of a case study of driving metrics and doing riparian monitoring on Fish Lake National Forest. And for that project, some of the co-analysts for that project was Jim Whelan, he's the fisheries biologist in the Fish Lake National Forest, and then Lena Schlechtling, who did the large bulk of this analysis. So I definitely want to make sure to give her a lot of credit there. For that case study that I'll be talking about later, I was more on a consulting role for that project. Yeah, so kind of the roadmap for this presentation is that I'm going to give you guys some context on the Forest Service's UAS policy, and so where we're at with UASs, using them, and the direction that we plan on heading. Then I'm going to talk about a handful of applications of UASs used within the Forest Service. Not all of them are catered towards riparian monitoring and mapping, but some of the approaches that we took to some of these applications can definitely be taken over to the riparian resource mapping side. And then I'm going to be going to the case study of deriving some different metrics of a devastated stream in Fish Lake National Forest from some flooding events. And then I'm going to talk about some partnership that we have with the Upper Deschutes Watershed Council and some of the current work that we're doing with them right now. So before I get started, I want to get some engagement with y'all. So hopefully Sam will be putting something in the chat box for this survey of how do you guys typically refer to remotely piloted aircraft. So I'll give you guys a second to enter those questions. Oh, wait, they're coming in. It's kind of a race right now. Quadcopters, drones, unmanned aerial systems. No votes for flying doohickeys. That's how I refer to it on my social media accounts. Flying doohickeys. Okay, so it seems like the majority of the community that we're talking about right now refers to these flying technology as drones. And I can definitely use that term as we're moving forward. But typically, when I refer to this new piece of flying technology, I typically refer to them as UASs. And the reason for that is because unmanned aircraft system kind of hammers home that it's a system and it's not just the drone platform itself. It involves a lot of other things other than just the platform, such as the controller, which is important, very important for piloting this platform. The sensor itself, which is how we acquire data with it. The software that kind of pilots the drone as well as processes the imagery. And then, of course, the pilot himself or herself or themselves, which they will majority of the pre-planning. And it's just a whole system. It's not just one thing. It's not just a drone, it's more than that, but definitely feel for everybody that just calls it drones. So to give you guys some context about UAS applications within the Forest Service, as of about 3 months ago, the Forest Service considered UASs the same as manned aircraft, which means that there's a lot of bureaucracy and a lot more paperwork that goes into being able to fly a drone within the Forest Service. But as of 3 months ago, we kind of changed some language within the Forest Service manual that allows us to fly drones not as manned aircraft, but kind of as something separate from manned aircraft. And currently, we are trying to spin up the UAS program within the Forest Service to allow for training and certification for internal Forest Service UAS pilots, and we're also trying to allow for forests themselves and regions within the Forest Service to acquire their own UAS platform so that they can conduct their own missions. This is important because up until this point, most UAS acquisitions within the Forest Service was done through what's called end product agreements or end product contracts, which is essentially a contract that the Forest Service writes up that says that, hey, contractor, I want 5 centimeter resolution imagery of this area, go get it for me, without any mention of using drones, UASs, satellites. It's just kind of leaving it up to the contractor to determine what the best methodology is for getting that 5 centimeter resolution imagery. And that's how most of the UAS acquisitions occur in the Forest Service. You can also contract for flight services going through the same procedures that you would have to do for collecting imagery using a manned aircraft, but that takes a lot of effort and for just acquiring some imagery over a small site. The Forest Service oftentimes goes through external partners as well, such as through universities or partnering with the BLM or with other nonprofits such as the Upper Deschutes Watershed Council that we're actively coordinating with, that they acquire imagery for us, and then we do all the analysis of the imagery. And then currently under development is training Forest Service UAS operators so that they can acquire their own imagery. So we're hoping that the amount of applications that we have within the Forest Service grows exponentially. So into applications of UASs, want to start talking about those. So as you can see in the next couple slides, that we've got a handful of examples of applications, even more than this within the last year that we've done. So you can do drought stress monitoring, dam inspection, of course, riparian mapping and monitoring. Got a handful of projects within the Pacific Northwest and the Intermountain region. Not a whole lot of applications on the East Coast yet. We've got some missions planned for the East Coast, but just haven't had a chance to start implementing those projects yet. But in the next couple slides, I'm going to be going over some of these examples in more detail. So this first example was what we were trying to do here for this application was interpret vegetation groups and locate groundwater springs within a fen wetland in Colorado. And what we did here was we had a RGB camera and a thermal camera acquire imagery over this area. And we did some automated classification of these areas, trying to detect different vegetation groups. But one of the cooler things was identifying these groundwater sources using thermal camera. So here in this example, we're looking at NAPE 1 meter resolution imagery. You can't get a whole lot of information from here, but with the UAS imagery, we got 1.5 centimeter resolution, and you can really see the individual vegetation groups in each example, in each area. With 1 meter, you can't really tell that at all. And then going over to the thermal imagery, if you approach this with the assumption that cold water or saturated areas are colder than the surrounding or a different temperature than the land surface, you can interpret that the temperature anomalies are where you have groundwater. And that's exactly what we did here. Another application was doing some grazing allotment monitoring adjacent to a stream, so a riparian area, assessing if we can see stubble grass height to try to argue or see if we want to make some grazing allotment changes. And this is important for the Forest Service because making any type of grazing allotment changes is pretty contentious from all sides. So we wanted to have another approach for trying to get this information and provide an argument that changes need to be made for different grazing allotments. And this project was done on the Starkey Experimental Forest in Oregon. You can do basic forest health monitoring. If you have like a camera that can collect in the near infrared band, you can get a lot of information about vegetation health. So you can tell what trees are being stressed either from a variety of different variables, drought or pest, or where there's just standing snags, and you can get all that information from a sensor that has collects in the near infrared band. And here we have the MicaSense sensor, which is about $7,000 currently. This is a really cool application where the forest managers of Cache National Forest knew that this embankment right here was becoming more and more prone to failing and resulting in a landslide. So what we had to do is we had to fly a bunch of parallel lines to get a lot of overlapping imagery so that we could create a three-dimensional product from the UAS imagery, so that they will be able to compare time 1 to time 2 from, like, if this stream embankment ever does fail, they can see how it failed. And another cool portion of this project was that we collected in thermal imagery as well. So we were trying to identify any seepage locations. So if there's any groundwater seeping through this embankment, we can tell where that location was occurring to maybe see if that had an impact on when this embankment fails. And this embankment in this image is located over here, so it goes right into a reservoir. Similarly, we can do take that same kind of approach that we did with that embankment and do dam inspections. So in Region 5 or California on the Angeles National Forest, we collected high-resolution thermal imagery of dams, trying to identify weak spots. So areas where there's like actual active water flowing over the dam, you can clearly see that in this thermal image. So this is cold water flowing through. But where there's not active water flowing through, but you still get these cold spots, you can assume that that's a weak spot. Water's coming through the dam that's not supposed to be coming through. And that's important information to have if you're an engineer and you need to make some changes to this dam, prep for, or maybe make some repairs, or maybe make some arguments that we need to remove this dam, etc. It's a pretty cool application. Another application up in the Pacific Northwest was doing some abandoned mine inventorying on the Willamette, Umatilla, Wallowa, Whitman National Forest, where we were trying to get an estimate volume of mine tailings of this abandoned mine. And we got a pretty good accurate estimate of how much sediment was here or material. And with that information, you can have make a bunch of different decisions, such as contracting how many truckloads you need to have for removing this sediment, or estimating how much leakage you're getting from these tailing ponds. A lot of information that we give to decision makers that we produce that then we just let them decide what they want to do with that information. This is another cool application where we're trying to map dinosaur footprints in Colorado. So this archaeological site was located right next to a stream, and this stream frequently flooded and deposits a lot of sediment. And before they did that, they wanted to get a good geographic representation of where these dinosaur footprints were located. So we had a really high resolution imagery. We had to fly this drone like 40 feet above the ground, which is, as far as drones and UASs go, that's pretty low to the ground. And we mapped where these footprints were, so that when this area does get covered with sediment, we still know where these dinosaur footprints are located. And actually, coming up this winter or this early spring, we plan on going back to this location and go to a new excavation location, which is located in this area, and mapping that area as well, so that they can allow that area to be flooded again, and then they'll probably excavate more area to get a good story of where these dinosaurs were going when they were walking across this area. With all of these applications, one of the most suitable kind of applications that I think are for UASs is riparian monitoring, for multiple reasons. So typical riparian applications are pretty small in scale, which makes it very cost effective to use a drone rather than using an aircraft or a satellite, because contracting an aircraft, a manned aircraft, to fly over a really small area is going to be really cost ineffective, just because of economies of scale. If you want your dollar per acre for the amount of area that you're trying to cover be economically lucrative, you need to cover a lot of area with that aircraft. Whereas with a UAS, you can send somebody out there with the backpack with their UAS or drone and acquire that area. And then typically within a week, you have your data, and it's pretty straightforward. Also, with the riparian areas, you tend to have quite a bit of changing environments compared to like other land cover types, like grasslands and mountain tops. You have a lot more changes that happen on an annual basis that drones can capture on a more frequent basis. And you can deploy a UAS after some geomorphological event, such as a flood or a landslide. It's really hard it takes a lot more time to contract an aircraft or get a satellite to point their sensor towards your area of interest, and maybe you'll have a cloud free day to acquire that imagery. Whereas UASs, those variables become non-existent. They become non-factors. So riparian monitoring, it seems like it's one of the best applications for UASs compared to using it for other resource mapping applications or reasons. So now I'm going to go into that case study that I was preferencing. So this case study was conducted on the Fish Lake National Forest in Utah, which is located in kind of south central Utah. You can kind of see some of the specs of this stream. It's a rather small stream with a small mean annual flow. It's pretty high altitude. Max elevation, you can get mean elevation here. Yeah, pretty basic stream. The reason that we wanted to start monitoring the stream was because in 2010, there was a very large fire where 1/3 of the watershed that was part of Fish Creek, or the reaches that we were looking at, had really high burn severity. All the microbes in that soil were killed, which means, obviously, you guys are probably aware that that causes a lot of concerns for erosion, for a lot of sediment to be deposited into the streams. And that's exactly what happened. In 2011, there was a nearly a 1,000-year flood event for this watershed that caused a lot of flooding. You can kind of just see some of the details here. I don't want to go through each one of these little points here, but you can see for yourself that it was a big event, and it completely killed off the fish population in the area as well. So they ended up, and then obviously there was a lot of concerns for down cutting, lateral erosion, channel aggradation, and then side tributary alluvial fans, all things that are pretty major changes within a stream environment. So they did a lot of stream restoration, and they focused a lot on trying to rehabilitate the fish populations. One of the things that they did was just that was a low cost approach of just dumping a lot of wood in the area to try to slow down the stream velocity, which has I'm sure you guys are aware of all the benefits of that. So what Jim Whelan came to the Geospatial Technology and Application Center was that he wanted to know the suitability of UASs for doing just riparian monitoring after all these restoration efforts were conducted. So he wanted us to develop techniques for IDing stream morphology changes, identify erosion sources, map aquatic and riparian habitats, and assess aerial stream temperature monitoring, and then document all this restoration, or give him a way to document restoration efforts. So when it came to that, up to us with that, we wanted to try to develop a semi-automated detection method of detecting large woody debris that they intentionally placed there. And then semi-automated mapping of in-stream features, so differentiating pools, riffles, and runs. Semi-automated method of land cover mapping. And estimate geomorphic change and identify bank features that are prone to erosion. And then assessing stream temperature. And the rest of the slides are going to be going over that. So getting into the data acquisition. So we used UASs, obviously. We had 2 different acquisitions, one using a DJI Matrice 600, and these are all end product agreements. And one was done by the contracting company that I work for, Red Castle Resources. And one was much higher resolution than the other, but both were very high resolution imagery. One was 6 centimeter resolution, one was 8 millimeter resolution. Both really high resolution imagery compared to like 1 meter resolution. And then we also had thermal imagery collected as well over this area. If you're wondering what a phantom looks like, this is what a DJI Phantom looks like. One of the reasons that we had 2 acquisitions was because the first contractor that collected the imagery did not take into account image blur in the image acquisition. So that's just when the drone is moving too fast for how quick the shutter speed is collecting images. So when it moves across the landscape and takes a picture, it's getting a lot of different pixels mixing in with one another. So you get this kind of image blur effect. So that these images are of the same area. And as you can see that the Phantom 4 imagery, despite being high resolution, is much more crisper. So we can identify these large woody debris much more easily than this Matrice imagery that suffered a lot from image blur. I'm gonna skip this just for the sake of time. When we were trying to create 3-dimensional products from this imagery, when we try to create it from the Matrice imagery that suffered a lot from the image blur, we got a lot of noise in the data. So this purple dot is in the same location on each image, but on here you can't really tell at all where this stream is. It's just filled with a bunch of noise, and that's due to this image blur. So we had to go in and recollect imagery of this area so that we can get better products and perform a better analysis. This image I like quite a bit because this purple dot is where these field photos were taken. And so you can kind of see that this drone imagery is giving you, I think, just as much information or nearly the same amount of information as these field photos, but on a much larger scale or smaller scale, however you want to refer to that as. Not going to go too deeply into the analysis that we conducted using the thermal imagery because it sounds like that's what you guys did a little bit last week. But we did collect thermal imagery for this project. And so there was quite a bit of field data collected for this project. We tried to identify where there was herbaceous cover, all these different land cover types, as well as subclasses for these different land cover types. And then these are also the different in-stream features that we were trying to classify as well using drone imagery. And we tried to perform this type of mapping all using a semi-automated technique called object-based image analysis. And if you're unfamiliar with object-based image analysis, basically what it starts out with is you delineating features that are similar in color. So this is kind of what it looks like. It kind of delineates the tree from the herbaceous cover. And in this example, I was just trying to do a simple classification where I was differentiating land cover from stream cover. And so what I was doing was I gave it the training algorithm a bunch of examples saying, hey, this is water, this is water, this is water. And saying that over here is land cover. This polygon is land cover. This polygon is land cover. This polygon is land cover. And then it takes that information and does a classification on it. And this is kind of the results that you can get from it. And so we applied that on a much more larger scale with all the different land cover classes, and you can kind of see the results right here.
Kain, this is Amy. You have just about 4 minutes to wrap it up.
All righty, I'll try to speed up a little bit. So this can be done in ArcGIS Pro, or eCognition. And with doing this type of land cover classification, you can kind of see the distribution of land cover types. And you can break like the herbaceous cover up into even further land cover types, such as breaking up between riparian herbaceous, upland herbaceous, or even transitionary herbaceous. There was a learning moment within this analysis between the Matrice 600 classification and the Phantom classification. So as you can see in the distribution of the land cover classes, that soil in using the Matrice 600 classification was quite a bit different than the soil distribution of the Phantom classification. And this is mainly due to the difference in resolution. Remember that the Matrice imagery was about 6 centimeters in resolution, and the Phantom was like 7 millimeter resolution imagery. This difference is important because when Lena was doing the analysis, she did not take that into consideration and kept the scale parameters the same when we were conducting this analysis in eCognition, so that it did not. So, for example, in the higher resolution imagery, what was happening was the soil in between this vegetated area was being classified as soil. Whereas in the lower, coarser resolution imagery, this area would have been classified as upland woody vegetation. And that's why you see this change in distribution of the land cover types. And so we performed this similar analysis for classifying these different in-stream features, riffle, run, cascade, pool. And Jim Whelan gave us some training data, not training data, some validation data for how well we performed this analysis. And based on that analysis, we were able to get about a 92% total accuracy based on the validation data that he gave us. So validation data that he collected in the field and through just manual interpretation. 92% accuracy as far as like an object-based image analysis goes is pretty stellar. Typically, you try to at least achieve 80% accuracy, so 92%, something that we're very happy with. Remember, this is a model. All models are wrong, so you can't really expect 100% accuracy. Another thing that we did was we detected banks that were more prone to erosion by just using the three-dimensional products that we derived from the UAS imagery and identified where any that were above 80 degrees. And then we manually went in and looked if they had any type of surface protection. And if they didn't, we can go ahead and tell the land manager, hey, there's this area might be prone to erosion. Do or do not anything for addressing this. Again, in my type of position, we don't make the decisions, we just kind of provide the data. You can also do geomorphic change. So in this example, we In this area, we had LiDAR data from 2014, and we compared it to the three-dimensional products created from the UAS imagery that was collected in 2018. And you can get a difference in the amount of volume between time 1 and time 2. You can see in individual areas. So this is areas where you see aggradation of sediment, and this is areas where you see erosion of sediment, which can be really important for Jim Whelan, our partner, said that this was really important information for him for assessing the rehabilitation of this area. And last thing, I just want to talk about a partnership that we actively have going on for work that we're actively doing with the Upper Deschutes Watershed Council, where we are trying to create an accessible methodology for deriving various metrics for stage 0 restoration monitoring using UAS imagery. When I say accessible, I mean readily available to a wide population. So like, for example, not a whole lot of people have access to eCognition, but a lot of people have access to like ArcGIS Pro. So we're trying to develop all these methodologies in ArcGIS Pro, and the different metrics that we're trying to create are like a land cover map, substrate size estimates, water surface map, and getting a count of large woody debris. Upper Deschutes, and the reaches that we're looking at are on the Whytooth Creek. In these locations, this is an active analysis going on. So we don't have a whole lot of results to present. If you're unsure where Whytooth Creek is, Sisters, Oregon is like down here, and I think Bend is up here in this area over here. So this is an ongoing project that we want to try to make sure that whatever protocol we end up deciding to create, trying to derive these various metrics, are going to be accessible to other people in the region, meaning the Pacific Northwest region, so that you guys can use it, Forest Service. So keep tabs on us. If you guys are interested in more about this ongoing project, feel free to contact myself or Lauren Mork from the Upper Deschutes Watershed Council. We'd be happy to give you guys updates on this ongoing project. And that's my presentation. Happy to answer any questions.
All right, thanks so much for a very cool presentation, Kain. We do have time for some questions. And just a quick reminder, you can either type your question into the chat, or you can use the toolbar and click on the hand icon to raise your hand, and we'll call on you to unmute yourself. And so it looks like, Russ, did you have a question? I see your hand is raised. All right. Russ's hand has been raised for a while, so maybe that's not intentional. All right. How about Eric? Looks like you have your hand raised.
Sure, Kain. I was wondering if with the RGB and thermal, if those were flown on the same flight, or if you did separate flights with each camera.
Those were done in separate flights. So you can do them in the same flight, but there was just some logistical issues that we were encountering that resulted in us doing them in separate flights. That's the short answer, at least.
Any tips on kind of bringing those two image sets together?
Like making sure that they're overlapped with one another?
Yeah, I guess if there's any tips on like orthorectifying thermal imagery versus typical RGB imagery, is there differences in using that, or?
Yeah, thermal imagery tends to be, just from experience, tends to be more difficult because just the nature of thermal sensors, they don't tend to collect imagery at the same resolution as spectral. So what you're trying to work with like less ground control points for trying to tie the imagery to a geographic location. Yeah, my colleagues have definitely worked with thermal imagery a lot more than I have, so they would be able to give you a little more tips than that. But all of our processing is done, most of our processing is done either through Pix4D or through Metashape. And I can't really think of any general tips, honestly, for orthorectifying thermal imagery. I can give you plenty of tips on orthorectifying RGB imagery, though.
Okay,
So
thanks.
Yeah.
All right, so we've got a bunch of questions in the chat, so we're not going to get through all of them right now, but I'll ask the first one, and then we can come back to these questions once we get to the open Q&A at the end. But so one more question for Kain. What is the height you are flying your flight, and what processing software are you using to stitch your imagery?
Yeah, so I need to look at the resolution of the imagery again. So for about 5 centimeter resolution imagery, you typically fly at 300 to 400 feet of elevation. But for this, we were getting about 1.5 centimeter resolution for this project on the Fish Lake, and we were flying about 150 to 200 feet, if I can recall. Again, this imagery was collected in 2018, and sometimes the details kind of get lost on me. So yeah.
All right. Well, thanks for a very cool presentation and for the questions. And hopefully we'll get to some of these other ones toward the end of the webinar. But now I am going to pass the microphone back to Eric while Lauren brings up her presentation.
Sure. Yeah. Next, I'm happy to introduce Lauren Burns, a fisheries biologist in the Fisheries Science Department at the Columbia River Intertribal Fish Commission. So I was able to see Lauren give a presentation in person at the last Oregon chapter of the American Fisheries Society meeting last March, which was the last in-person scientific conference in the world, maybe. But Lauren leads CRITFC field efforts in the Grand Ronde Basin in Northeast Oregon, where her group has been working to test and develop a new status and trends monitoring tool that utilizes unoccupied aircraft systems. Originally from Ohio, she earned her BS in Fisheries and Wildlife Management from Ohio State University, I guess that's the other OSU, and an MS in Environmental Science from Washington State University. Lauren has also worked with the Oregon Department of Fish and Wildlife. She was conducting Columbia Habitat Monitoring Program surveys, which we heard a little bit about last week, in the John Day Basin, and she worked as a water quality and flow monitoring coordinator in Michigan. Today, Lauren presents an overview of CRITFC's Tributary Habitat Assessment Protocol. Thank you, Lauren. It's all yours.
Hi, thanks, Eric. Thanks for the introduction. I just want to make sure, can you guys see my slide?
Yes, I'm seeing it.
Okay, great. And it's in presentation mode and not in presenter mode?
Yes, it looks great.
Okay, great. Okay, well, thanks again, Eric, for the introduction. And I want to just thank PNAMP for inviting me to give this presentation and promote our newly developed habitat protocol that we've been working on since 2018. And before I dive into the presentation, I'd like to take a moment to acknowledge my co-authors and co-workers on this work. So Casey Justice, Seth White, and Ben Staten with Columbia River Intertribal Fish Commission have all been very helpful from analysis to fieldwork implementation and have been involved in this project since 2018. So without further ado, I'm going to dive into the presentation. I'm going to be presenting on integrating unmanned aerial vehicles into large-scale habitat monitoring in the Columbia Basin. So just a little outline of the presentation that I'm going to be giving today. I'm going to talk a little bit about the history and motivation as to why we decided to develop a new habitat monitoring program incorporating remote sensing methods. Go over a case study that we conducted in the Grand Ronde Basin in northeastern Oregon. And then finally provide an overview of the protocols it stands that we'll be implementing and testing on the Upper Grand Ronde and Catherine Creeks, hopefully in 2021, barring no further COVID restrictions. We were actually supposed to test out the protocol this past season and forewent as a safety precaution. All right, so just a little bit about CRITFC, or the Columbia River Intertribal Fish Commission. So CRITFC's mission is to ensure a unified voice in the overall management of the fishery resources, and as managers to protect the reserve treaty rights through the exercise of inherent sovereign powers of the tribes. They do 4 ways. And these are done through a variety of departments within CRITFC. So the first is to put fish back in rivers and protect the watersheds where they live, protect tribal treaty fishing rights, share salmon culture, and provide fisher resources. Portland has 2 offices. I work out of the Portland, Maine office, and we also have a genetics lab in Hagerman, Idaho. Today, I'm going to be talking about my work in the Fishery Science Department, which, as I mentioned, works on putting fish back in rivers and protecting watersheds where they live. Our work in, within the Fishery Science Department, I work within a group called Habitat Group, or Watershed Sciences to some within the organization. Our work has primarily occurred in the Grand Ronde Basin on Confederated Tribes of Umatilla Indian Reservation land and lands historically used by the Cayuse, Umatilla, and Walla Walla tribes. All right, so a little bit more about our Habitat Group. So my work within the Habitat Group serves in the Habitat and Biotic Assessments component, which is that first year. So we collect data on the ground, which has historically been collected using the Columbia Habitat Monitoring Program in the basin. So collecting habitat and biological data, doing empirical studies of riverine and food webs, and then generating metrics, which can be indicative of limiting factors. So these raw kind of fine scale data feed into riverscape analyses, where we extrapolate limiting factor metrics to population scales, evaluate larger land use and climate impacts, quantify effects of cumulative restoration on limiting factors. And all of this feeds into one of our broader objectives within the Habitat Group, which is developing a life cycle model for spring Chinook salmon to evaluate benefits from aggregate restoration efforts. And an important component of our work is this adaptive management cycle. So throughout each of these project components, we then go back and reevaluate whether these quantitative objectives for limiting factors are met, and communicate these results to implementers, and cycle back and reassess management actions and research questions. So a little overview about monitoring advancements. Monitoring has changed dramatically over the course of just 100 years, since the early 1920s when general land office surveys were occurring. We were primarily reliant on pure manpower, yet technological advances, such as sophisticated total stations, which we used for the Columbia Habitat Monitoring Program in the 2010s up until 2017, and now to drones, have substantially increased the amount of ground crews can cover while decreasing the time and effort, and therefore, in some instances, costs. So with technological advances, we have new exciting opportunities to link data from multiple spatial scales. So starting at the landscape, we can look at some of the trade-offs between spatial extent and resolution, accuracy of data, and the distance at which these measurements are collected at these multiple spatial scales. So for starters, as we've heard in previous presentations, satellite data are common, although they have a larger spatial extent and resolution. They have, in some instances, reduced accuracy because of their distance from the ground. Next up, we have something like measurements or instruments that would be attached to small aircrafts or helicopters, such as LiDAR acquisitions or FLIR acquisitions. These happen at kind of intermediate spatial scales, but we also have heard that they can be rather expensive. And onto drones. Drones represent an even finer spatial scale. You're more limited in your spatial resolution, the area that you can cover, as well as the potential accuracy of the instruments as they exist to date. And finally, what I've had a lot of experience with in the past are doing really intensive, highly accurate ground-based surveys, which don't allow you to cover a lot of ground, but like I said, produce very accurate data. So these would be total station surveys, terrestrial laser scanning surveys, or RTK surveys. So now I'm going to go over a case study that we implemented in the Grand Ronde. And so we implemented this case study to better understand how we might be able to continue status and trend monitoring in the Grand Ronde Basin while addressing some of the major critiques of the CHAMP program. So we designed a pilot study that sought to evaluate the effects of canopy density and geomorphic type, which I'm calling reach type here, on UAV-derived data products and metrics. And I'm just going to preface this by saying, to save time, I've previously presented this research a number of times, as Eric mentioned, at Oregon AFS and other webinars. So I'm going to kind of gloss over this. And if you'd like more information, my email is in the last slide, and I encourage you to reach out and contact me to talk about this more. So the case study in the Grand Ronde Basin, we applied 3 different classification schemes to select study reaches for this to evaluate the effects of canopy density and reach type. So the first was watershed size, small or large, reach type, constrained or unconstrained reaches. And the third was canopy density. So these were binned into sparse, medium, and dense classifications. And this helped us to evaluate some of the limitations that might occur in redesigning a monitoring program that is less reach-based and more continuous, allowing us to see the decreased resolution, decreased accuracy that potentially could come as a consequence to increasing canopy density or changing geomorphic conditions. Our selected study reaches were, as I've mentioned, on the Grand Ronde River and Catherine Creek in northeastern Oregon. We had 13 reaches within these 2 rivers. These reaches were also previously monitored as part of the Columbia Habitat Monitoring Program, which used a GRITS-based design for site selection. And for this initial study in 2018, because drones were fairly new for use in monitoring, we preferentially selected reaches that were on U.S. Forest Service land, just for ease of access and getting our program established without maybe upsetting partners or landowners in the basin. Okay, so just a quick wrap up from the case study before I dive into the implications of the case study that led to the redesign of our new habitat protocol. So the limitations that we learned from the case study, you're collecting extremely large data sets, and these data sets need to be stored somewhere. They're stored primarily on hard disks, hard drives, but eventually need to be securely backed up to a cloud location. And quickly accessing, assessing those files is difficult. Takes a long time to upload and download. Similarly, post-processing is lengthy, and I'm sure you all know is computationally taxing. You need a high processing computer, you need to be a skilled coder in some instances. Richie Carmichael mentioned this last week in his presentation, but we've yet to define data standards or metadata standards. So there's some unknowns still in this field of research. There's also ongoing regulatory changes. Contract work and or custom sensor integration has proven difficult, even in the Portland metro area. We had a dual gimbal mount designed and installed on our Matrice 600 Pro, and had to work with a contractor who was actually an electrical engineering student at Oregon State University. So there's a market need for, I guess, electrical engineers to contract with in the area. And another limitation was just our presence in the Portland metro area. We had local flight restrictions. It's difficult to find areas locally that we can safely fly that aren't, within flight restricted areas, such as airports. And then we also found that canopy density does prohibit measurements. And from that, we decided that, we're going to continue to count large wood on the ground. Increasing canopy density increases the shadows cast onto the stream and onto the landscape, which can therefore affect the accuracy and resolution of the data products. And one of the primary objectives of the study was to test out whether or not we could accurately obtain bathymetry from structure for motion. And the consensus on that at this time, and with the sensors that we have available, is that it's not suitable for continuous surveys. So some of the strengths of the study that we learned, or some of the strengths that we learned from the case study. So UAVs provide a flexible framework for conducting monitoring. They allow for future data reanalysis. The data holds their value over time, and as new software and post-processing algorithms come on the market, it could be reevaluated at a later date. There's significant reductions in the amount of time required for sampling, albeit those might be made up for in the post-processing time. There's an overall decreased effort and time. So you're getting more continuous surveys and more ground covered. And another critique of some previous monitoring programs is there's a potential reduction in the variability of measurements. So these are variability between crews and between years. And lastly, as we've kind of all noticed, you're getting highly visual data sets. So these linked data offer very compelling visualizations that are easily understood by a variety of stakeholders, and great in presentations. So here's just an example of how we're able to link and visualize habitat data on the ground with ground collected data and data collected from the air. So this figure is just showing channel units laid out for a given segment and the different channel types. Okay, so now on to our tributary habitat assessment protocol. So our goal with this protocol was to strike a balance between rapid, large-scale monitoring protocols such as aquatic inventories with those of intensive reach-based surveys such as CHAMP or PIBO. So this protocol is based on a need to balance intervals at which monitoring occurs. Emergent technologies like drones and advanced sensors have made it possible to cover larger areas in shorter amounts of time, which loosens previous restrictions of monitoring based both at the rate at which ground can be covered by crews and the desired resolution of the data. This protocol, as we've designed it, allows for the assessment of fish habitat conditions across a range of potential spatial scales, from geomorphic channel units, such as pools, fast water turbulent areas, fast water non-turbulent areas at lengths from 1 to 100 meters, to reaches and segments up to half a kilometer. and even at whole network or watershed scales. So this protocol is meant to address tributary habitats. So these are wadable streams and rivers. It's based off of, like I mentioned, widely used and accepted regional protocols, such as aquatic inventories and the Columbia Habitat Monitoring Program. Using drones for monitoring means there's increased reproducibility by limiting the number of ground-based measurements, which also equals less time spent on the ground by crews and reduction in crew variability. We've focused on methods in this protocol that are quantifiable and repeatable, while excluding those that are more subjective. And advances in monitoring methods, drones advance monitoring methods by incorporating these new and emerging technologies, which is why we're all here on this presentation, and helps fill the data gap at these intermediate spatial scales from, intensive, narrowly focused ground-based surveys to kind of Cessna, helicopter, or satellite data. So our protocol, as I'm going to outline, is broken down into 4 stages: fieldwork, data processing, output, and metric generation. Onto the ground-based component of the fieldwork. So as you know, this is a fish habitat survey protocol. It involves collecting georeferenced channel units using a sub-meter GPS, collecting additional auxiliary habitat data, and laying ground control, a limited number of ground control within a kilometer for georeferencing aerial imagery. As I mentioned, they're continuous surveys. They can be done with a 2-person crew, the ground surveys. We've really pared down the measurements, which means limited equipment is needed, allowing crews to cover larger areas. And we've incorporated a threshold of 25%, where if canopy cover is greater than 25%, and may prohibit imaging the channel, crews are instructed to collect additional ground information. So this might be about channel unit geometries, or the location of left or right wetted edges. The types of data that we collect on the ground are done so at the unit scale, which I've already mentioned. We collect information about unit boundaries, which are georeferenced, and geometries. We collect depths, in total of 9 for each channel unit, or 11 in pool units. We conduct large wood counts, look at undercut banks, conduct bankful cross sections, quantify substrate sizes, and continue to evaluate water temperature. The aerial component of this protocol involves planning a flight mission, collecting imagery, looking at those images to conduct initial quality check, exporting camera coordinates. The platforms that we use to conduct aerial field work thus far have been DJI Imagery 600 Pro. We have a ZenMuse X5 visible spectrum camera, RGB camera, and also a MicaSense Red Edge multispectral camera. We recently purchased a DJI Mavic 2 Pro as well that we have yet to test in the field, but significantly smaller than our workhorse of Matrice. That's the Matrice 600 Pro. For flight mission planning, during 2018, we primarily used DJI Ground Station Pro, and we'll be using Litchi moving forward. Some considerations for the aerial component of the fieldwork are pre-flight reconnaissance and obstacle identification. It's important to actually have your boots on the ground, identify obstacles, look at the max vegetation height. We are typically flying at between 80 and 120 meters in the Grand Ronde Basin. Some suggestions that we found are helpful in obtaining better data products are flying close to solar noon, which reduces shadows, collecting multiple viewing imaging angles, and using converging flight lines, using a polarizing filter to reduce glare on the surface of the water. And then also, I'm a stickler for protocols and safety measures. So it's important to adhere to regulations, document your flight plans and develop emergency response plans. So always make sure that you have a certified pilot, you're insured, you're logging your flights, and you're filing your flight plans as necessary. So on to data post-processing. From the ground-based portion of the fieldwork, we're able to use the channel unit georeference channel units and ground control points. And we export that data, and that's used as an input when we're running our image alignment and georeferencing algorithms. So we do all of our post-processing of drone collected imagery in Agisoft Metashape, previously Agisoft Photoscan. And the images get run through a series of algorithms. The first being a scale invariant feature transformation, SIFT. Second, structure from motion. Third, multi-view stereo matching, which aligns images taken at different imaging angles or altitudes together. We then use Cloud Compare in some instances as an additional tool to remove vegetation. Agisoft doesn't, at least in 2018, didn't do a great job of removing, hanging branches close to the ground level, and Cloud Compare works pretty good for that. We use ArcGIS to manually edit channel unit geometries that were collected with the 7-meter GPS. I'm glad Kain gave an introduction to object-based image analysis because we're also using object-based image analysis with eCognition to automate the post-processing and automate feature extraction. And then finally, some work is done in R, which is we've designed a number of custom scripts that aggregate data over various spatial scales and then produce metrics. So the desired data products and metrics that we're interested in getting from this protocol are digital elevation models, orthomosaics, and dense point clouds. And we've limited them to those three because we feel that that's it's fairly easy for an inexperienced data processor to get from this post-processing regime. From these data outputs, we're then interested in obtaining 10 directly derived metrics from sense data. The protocol in general lists 30 metrics of interest, but there are 10 metrics that we're interested and viable to get from imagery as we've tested with the sensors that we have.
Hey, Lauren, this is Amy. You have about 5 minutes to wrap up.
Thanks, Amy. So future directions, as I mentioned, we're going to be implementing this protocol in the Grand Ronde Basin in 2021, hopefully, fingers crossed. We're going to be working on linking data and computing metrics across spatial scales, and that's something that Richie at Biomark had mentioned. So there's a commonality there. We've also collected or had contracted with Quantum Spatial to collect topobathymetric LiDAR in 2020. So that'll be one data set that we're also going to be comparing to future data sets that are collected from drone imagery. With this topobathymetric LiDAR, we have historic data that we can then go back and look at change detection, but that's from a terrestrial LiDAR flight, so there's some limitations there. We need to continue working on developing automated workflows for post-processing. It's challenging, especially because there's no data standards as of yet. And we'd like to purchase some additional sensors. We've talked about FLIR and LiDAR sensors, and maybe looking into those in the future. And then I've also been talking about working towards developing regional standards and practices for using UAVs in monitoring. And Sam, if you wouldn't mind throwing that link into the chat, we'll do this Menti poll really quick. So the question that I was asking for this poll is, would you or someone within your organization be interested in joining a technical work group to develop common UAV standards and practices for the Pacific Northwest? And we have votes coming in. Some people saying no. That's okay. Seems like there's a lot of interest. I mean, as we've seen in this technical webinar series, there's been a lot of interest in developing these data standards. It seems like most people would be interested in sitting in on something like that. All right, I'm gonna go back to presentation now. And finally, just some acknowledgements. I'd like to thank past CRITFC and Champ crews for your hard work out in the Grand Ronde Basin and out in the Columbia River Basin as a whole. The permitting help that we got from the U.S. Forest Service for our work in 2018, Blue Mountain Dispatch, and being patient with us and figuring out our flight planning and notification process, and finally our funding sources. The BPA Fish Accords and some of these funds to purchase the drone came from BIA. And I'd also like to give a special thank you to any of you that might be on the call that I've talked to in the past about your monitoring using drones and your advice, because they've been really influential in getting our monitoring program off the ground. So thank you. And with that, I'll take any questions.
All right, great. Thanks so much, Lauren. That was a great presentation. And we have plenty of time for questions. So again, if you want to either type your question in the chat, or you can use the toolbar to raise your hand, and we'll get those questions to Lauren. So let's see. In the chat, we have a question. Do you have a field protocol / checklist, and can you share it?
We do have a field protocol checklist, and it's in the appendix of our protocol. And I can share that directly with you, Kain. I think I already have your email.
Okay, great. Another question from the chat says, Beachy work well for grid mission flight planning?
So Litchi requires a little bit more time investment into planning your flights on the front end. You're able to set different camera angles at a given waypoint. So you're essentially, it's like building a PowerPoint presentation. You're essentially building in all of these different, I'm going to call them animations because I'm talking about PowerPoint presentations. You're building an animation. So one animation would be like, take an image nadir, so looking directly down. Then at that same point, adjust the camera angle to offset at 20 degrees, and then take another camera angle. But once you kind of have that developed, you're kind of able to use that as the basis for future flight plans.
Okay, great. Thanks, Lauren. Are there any other questions for Lauren specifically? All right, Eric.
Hi, Lauren. So I was wondering, you showed in one of the figures, it looked like you were doing some transects with depths on the ground. And I was just curious how you match those transects up with the orthomosaics and things like the products from the air.
Oh, yes. So I've done that in a number of ways. So that's one of the automated scripts that I've written in R, which essentially creates, you can use each of those points that you've collected on the ground. We've typically used those points, created a buffer around them, or selected the point that's nearest to that, and then taken the average of the structure for motion points in the area. You could also do that with the DEM. It's just a difference in data product. If you want to work directly with the dense point cloud, or if you want to work directly with the digital elevation model. I guess it's probably simpler to do in ArcGIS because you're just able to extract that information directly, the elevation value from the DEM directly to your feature class, as opposed to doing it in R. Hopefully that answers your question.
Well, I guess I'm curious because we have the point cloud or a DEM. You know what the stream looks like, and those measurements are pretty accurate. On the ground, you've got a tape or a stick or something, and I guess I'm just curious. You've got that measurements of width from on the ground, and just how you match up exactly where that is on the, I think it's the next slide, where that is on the orthomosaic, because you've got a series of points there that, how do you reference them together, I guess was the question.
So you're talking about the orthomosaic that from the drone imagery with the dense point cloud?
Well, I guess if you could go to the slide where we had those transects with the little X's, I think were depths and things like that.
Oh, yes.
Yeah, so you've got like that unit perimeter is something you could get from the orthomosaic, but then you've also got, I think those gray lines are something you captured is that something you captured on the ground or?
Mm-hmm. Yeah, so the only georeferenced information that we're collecting on the ground are the unit boundaries, and left and right wetted edge information, so that we can get further, a better idea of what the geometry of the channel unit looks like. So the lines, the wetted with lines, and the depths are not georeferenced. So we're just getting an average of what the conditions look like for that given channel unit. And that's one of the sacrifices that we've made to make this protocol more rapid. With the Columbia Habitat Monitoring Program, as you know, it was intensive total station-based surveys. So we were spending 3 days in the stream with, total station getting really accurate data about the location of each of these points. This is similar to AQI surveys, which is giving you an idea of the average condition over larger swaths of, the land for each channel unit.
Okay, great. Yeah, I understand that. Thank you.
Mm-hmm.
All right, Lauren, I have another question for you from the chat. What was
Sure.
the learning curve like for the post-processing?
So there's some information. It depends on, I can only really speak to Agisoft Metashape, but USGS published a few manuals that I used early on and made some modifications to. And those manuals are both available for Metashape using regular visible RGB imagery and also multispectral imagery. So those are really helpful. I think that probably answers it, but yeah, there's a decent learning curve.
Okay, great, thanks. And I'm gonna go ahead and open it up to just the open Q&A. So questions for either Kain or Lauren. And I'm actually gonna dig back through the chat because there were a number that we didn't get to with Kain. So Kain, this one's for you. Are the stream temperatures from the FLIR representative of surface temperature only?
Are the stream temperatures? Yeah, I understand that question. Could you say it again?
Are the stream temperatures from the FLIR representative of surface temperature only?
So the surface temperature of the water as opposed to, the entire water column.
Yeah, it's only surface temperature. For some reason I was thinking about like land surface, but yeah, it's only the surface of the water. There's not a whole lot of like penetration that thermal infrared has through the water column. So like it's only stream temperature, surface temperature.
And surface temperature, okay. And then related to that, they want to know at what resolution for the thermal imagery.
Thermal imagery, I believe, was 15 centimeter for the imagery that we captured.
Okay, thanks. And then Brent, you have your hand raised. You want to ask a question? You're on, oh, yeah, you're on mute. So I'm not, oh, okay, hand went down. Let's go back to the chat. Let's see. Let's see, have you gone back to these sites and successfully compared more than one set of surface from different years / time steps? Because I'm not sure who that's, if that was intended for Lauren or Kain.
I feel like that question was posted right before you opened up the question for everybody. So I think it was for Lauren, although I could answer it too.
Okay.
You can go ahead,
It's
Kain.
for both of you. You guys can both answer it.
Sure. So, for example, we've compared, so since UAS technology is so new, there's not a whole lot of opportunity to compare multiple acquisitions over time. But what we have done, like I said, I mentioned this in my presentation, is that we compared the digital surface model that we created from the overlapping UAS imagery to LiDAR imagery to try to see if we can estimate the amount of volume change that has occurred over between those two time periods. And you can do that with NAPE imagery as well, or any other image source. But we haven't had a whole lot of opportunities where we can compare multiple UAS acquisitions over multiple time periods. But that I'm expecting that's going to change very shortly once the Forest Service has a fully operational UAS program.
And I can just follow up and say that we haven't either. That was kind of a side project that I was hoping to do this past 2020 summer in the Grand Ronde, was do a quick revisit flights of a few of the sites that we surveyed or mapped with the drone in 2018, and look at, change detection or lack thereof over time.
Okay, thanks. So this was originally, I think, for Kain, but I think either one of you could answer. How do you get around shadows in forested streams?
Flashlights.
Yeah, don't have shadows.
Yeah.
Try everything to not have shadows in the imagery.
Collect at solar noon. You mentioned that, Lauren, in yours, that's just a basic protocol. Well, our typical rule of thumb is trying to collect at 2 hours on either end of solar noon. And solar noon is something you can find when it's not always at like 12 p.m. Yeah, sometimes it's at like 3 o'clock or 1 o'clock. So you just have to look up what solar noon is for that location and then hope that you have minimal shadows. something that we did find out recently was that due to the wildfires, it caused lighting to be really diffuse on our project area, which made no shadows exist at all, which was a really cool, I don't know, finding. So we were able to start collecting imagery at like 9:30 in the morning with no shadows at all. So maybe collect imagery while there's a bunch of wildfires going on.
All right. Let's see, another question. Did any of the flights occur over private lands? And if so, what percentage of landowners gave permission or were waivers for over 400 feet AGL used?
Do you want to take that, Lauren?
Well, we did have a couple sites. I know I spoke about there was a primary occurrence of our sites being on U.S. Forest Service land. A couple of our sites did happen not on public lands. One was mainly over near a wastewater treatment center in the town of Union, but we did image some of the surrounding private property. We didn't get explicit permission in advance from the landowners, but our interactions with the landowners at the time of flight were overall positive, which we weren't expecting. But that is another topic of interest. I haven't seen good agreement on the protocol for when and where to contact landowners and the legality of that.
Yeah, and for me, we avoid flying over. It's mostly always over Forest Service land, and Forest Service land is in Class G airspace, so we know that we're allowed to fly imagery over there. Plus, we're kind of told that we should fly imagery over there as a contractor. Yeah, and as far as the above ground height goes, we don't try to fly over 400 feet at all, but we do use the principle of if you're trying to image a radio tower, for example, and it's 600 feet tall, then you can fly that drone 400 feet above that radio tower that's 600 feet tall. So therefore, you're flying actually 1,000 feet above where you took off from. So we use that to our advantage as well, which is within FAA Part 107 guidelines.
All right. Well, I think that wraps up the Q&A. Thanks so much, everybody, for participating today and for the interesting questions. Thanks to Eric for helping be a host today. And then a big thanks to our speakers, Kain and Lauren. We did record today's webinar, so you can watch it again, or if you know someone who might be interested, you can share it with them. The video will be posted to PNAMP's YouTube channel, and it'll be linked on the ETIS landing page. The next webinar in the series is next Tuesday, October 20th at 1 p.m. Pacific, and we'll hear from Misha Hay from Quantum Spatial, and Phil Roney from Kramer for Sciences. And they're going to be talking about LiDAR and other remote sensing options for characterizing and assessing fish habitat. So we hope that you'll join us for that. And then the last thing I wanted to mention is that we are planning an emerging tech multi-day face-to-face event for late 2021 or early 2022, assuming it's safe to do so from a public health standpoint. And so at the end of the aerial monitoring sessions, we'll be sharing a questionnaire to get your input to help shape the content and format of the face-to-face event. So if today's presentations had you thinking you really wanted to know more about a particular topic or spurred an idea that you think we should follow up on, maybe perhaps Lauren's idea for UAV standards and practices would make a good topic for a face-to-face. But anyway, if you have ideas, we'd love to hear from you. So keep an eye out for that questionnaire, and we'll be sharing that during the last week of October. So that concludes today's webinar. Thanks for sticking around to the end, and have a great day.